This is the seventh video in the series, Quantum Mechanics for Everyone. And up to this point, we have been discussing the historical development of quanta concepts. In the last two videos, we explored de Broglie's hypotheses about matter waves or particle waves. It has now been exactly 100 years since de Broglie's doctoral thesis. However, there is still one thing we don't understand. Why did de Broglie conceive such an idea? And what was the state of physics from 1905, the year of Einstein's photoelectric effect, until de Broglie's hypothesis in 1924?
These 18 years or so were the years of Einstein, Niels Bohr, and Sommerfeld. We begin from the year 1906. Albert Einstein, again, used the quantum idea to explain the heat capacity of solids. But why? In classical statistical physics, the prediction was that the heat capacity at constant volume is independent of temperature. Heat capacity is the amount of heat to take off or to add to a system to raise its temperature by 1 degree. It's generally given by this formula when the volume of the material stays the same. Actually, heat capacity is the fancy name for how fast an object exchanges heat with its surroundings. The faster an object exchanges heat, lose or gain, the smaller its heat capacity, and vice versa.
In classical statistical physics, there is a famous law of energy distribution called the Equipartition Law. Consider a solid of n small identical atoms, each of which can vibrate about its equilibrium position. This law demands that each of such atoms should have by thermal equilibrium an amount of energy equals to 3 kBt, where kB is Boltzmann's constant and T the temperature in kelvins. Since we have n of such oscillating atoms, the total energy of the solid should be 3 times n times kBt. Now, if the volume stays constant, this energy E is the same as the heat energy Q contained in the object. Hence, if we substitute into the heat capacity and apply the derivative, we get the heat capacity to be dq over dt equals du over dt equals 3n kb.
Notice that we didn't mention any specific material by itself. We simply got a law that only contains n and a constant. This n could be Avogadro's number, representing 1 mole of the material. Therefore, classically, all materials would have the same heat capacity per mole. Don't worry, this seemed too easy to derive, unlike most stuff in physics. But it doesn't mean it's totally wrong. Actually, at room temperature, so many solids obey this law. It's called the Dulong-Putty law. However, it's not enough. The classical theory fails in predicting what happens at very low temperatures. Experiments show the heat capacity to behave like this at low temperatures. It goes to 0 when T approaches 0. There is a temperature dependence the classical theory cannot predict.
Einstein's solution goes like this. We should look at the atoms as harmonic oscillators, whose oscillation energy is quantized. Like in the quantum hypothesis of the blackbody radiation, each oscillator of these has an average energy of an integer multiple of the quantum energy, h times f, where f is the frequency of the oscillation. To simplify calculations, Einstein assumed the oscillators to be independent of each other, and all of them have the same frequency. Call it f. Now, if we used for small n the Planck's formula of quanta distribution from video 1 of this series, and multiplied it by the factor 3n, 3 dimensions and n oscillators, we get.
This is the total energy of a solid that Einstein got. It's not linear in temperature. So there is hope that if we differentiate it with respect to T, to find the heat capacity we'll get. And as we can see, there is a temperature dependency in it also. This theta sub E is Einstein's temperature. We can find it for each kind of material by fitting the formula to the experimental data of that material. Its value found to be few hundreds of kelvins. Let's plot C sub V against the temperature for copper. Einstein's formula predicts that c goes to 0 as t goes to 0. It also has a fair agreement with the experiment for t much higher than Einstein's theta. However, between 0 and theta, meaning at low temperatures, the agreement is poor. Usually, the heat capacity approaches 0 as t cubed, actually.
Well, one important reason for why the agreement is not that great is that these oscillators in a solid aren't independent at all, as Einstein assumed for simplicity. In fact, they oscillate collectively and transmit waves through the solid. This correction came by Debye some 7 years later. We'll continue to discuss the pre-de Broglie developments till we reach the point where we have no choice but to apply the de Broglie hypothesis of videos 5 and 6. Stay tuned, don't forget to subscribe to continue this journey, and thanks for watching.